This video is about the conical pendulum, which is what you're looking at. You've got a blue sphere, and it's attached to a string with a tension T. The sphere is a weight W and has an acceleration A. The tension on the string provides, if you break it down in the XY direction, it both supports the weight of the pendulum. Notice the pendulum bob, that round circle, is moving in a horizontal circle in this conical pendulum, and the vertical component of the string supports the weight. There is no vertical acceleration, it supports the weight, but the horizontal component of the string provides the centripetal force. This pendulum is going at a constant speed, but not a constant velocity, because the velocity continually changes, because the direction continually changes. In this video, we'll look at the physics of the conical pendulum. So, this is the conical pendulum. Two positions, a left and right position. In this particular pendulum, we have, it's a 1 meter long pendulum, so the string is 1 meter long, and its mass is m. It's moving in a circle that has a diameter of 1 meter, so that means that the radius is 0.5 meters, and this distance over here is also 0.5 meters. So we want to I'm going to look at the physics of this pendulum by drawing the free body diagram, and later on when we go down there, we'll just watch right now. Later on we'll go down and do it again down below. So we have the pendulum bob, they call it, has two forces on it. The weight force, which we'll call mg, because the mass of the bob is m, and it's got a tension T. This is T, and well, if this is theta, then this is theta over here, right? Right, you can see that's theta. This angle over here is theta. So, in order to analyze this, we'll break it down into its components. You've got some of the forces in the y direction equal 0. Why? Because there is no vertical acceleration. Vertically, it's moving in a horizontal circle. There's no vertical acceleration. So what we like to say is the up forces equal the down forces. Well, let's say the down forces, which is mg, equals the up force. Now that's the vertical component of this tension. So it's actually the vertical component, oddly enough, is t cosine theta. Why is the vertical component cosine? Take a look at this picture, and you can see that the vertical component is the adjacent side to the force, so it's t cosine theta. We can stop right there. Let's do a further analysis and say the sum of the forces in the x direction equal not 0 but mv squared over r. We could also say ma, but I think we're going to say, for this problem, we'll call it mv squared over r. That is the centripetal force. The sum of the forces equal the centripetal force, the force that's changing the direction of this pendulum bob. So what is the centripetal force? It is the, now look at this picture again, the centripetal force would, let me do something over here. Let me break this component down. Tension force has a vertical component, and it has a horizontal component. Let's put that over here, you can see it better. So we're breaking the tension down to its two components, and you can see it's the horizontal component down here on the bottom that is providing the centripetal force. Since that is the side that's opposite, if you look at this theta, these two thetas are equal. It is the side opposite, so it's the tan is the sine. So t sine theta is the only force acting in x direction. It's acting towards the center, equals m v squared over r. The t sine theta, so the only force in the x direction is t sine theta, and it equals ma, or mv squared over r. Let's put a box around these two. So these are the two equations we have. One equation comes from the sum of the forces in the x direction. One of the equations comes from the sum of the forces in the y direction. And oftentimes when we have sine and cosine, we know that sine over cosine equals tangent. So let's simplify this. Let's pull this equation over here, make it t sine theta equals m v squared over r, and the cosine equation, let's flip it over and make it t cosine theta equals what? It equals mg. So we're dividing the sine equation, put the sine equation in the numerator, the cosine equation in the denominator. We're dividing these two equations. We can see t goes away, t for tension, and you get tan theta equals, let's see, the m's cancel out, and you get equals v squared divided by gr, because what we could do is, let's multiply both sides by 1 over g, and that makes this go away, and we could see that this is you could call it the conical pendulum equation. Conical pendulum equation, tan theta. I don't know if this is not going to be on your reference table, but it's something that you should be able to derive. Let's make that r a little bit better. And this is all new to you, so let's do this all over again. Let's review what we said. What we said is that there are two forces on the pendulum bob when it's on the left. These are the two forces. There's the tension, and there's the mg. There's our free body diagram. So that's the free body diagram for the pendulum on the left side. What's the angle theta? Well, the angle theta, let's do it again. We know that this is the sum of the forces in the y direction equals 0. There's no y acceleration, so we already established that this is theta, because that was, we were told, is theta. So what is the up force? The up force equals the down force, so t, this is t cosine theta. See that cosine because of the angle we're given. We use cosine. The up force equals the down force. And then we say the sum of the forces in the x direction. They could equal ma, or we could say m v squared over r. So the only force in the x direction is t sine theta, because it's the opposite. This component over here is the centripetal force. This is the only x component. So t sine theta equals m v squared over r, or ma. And then what do? We took the two equations, t sine theta equals m v squared over r. We put it on top of the cosine equation. T cosine equals mg. And then we cancel. Sine over cosine's tan theta equals v squared divided by gr. You have to be able to generate that equation. Find the angle. Well, there it is. Find the angle theta. So it's the inverse tan of the angle theta is inverse tan of v squared over r, v squared over gr. That is. Now I remember. Find the angle theta. Well, that's just trig. Let's take a look at this picture over here. We know the opposite and the adjacent of the hypotenuse, because they told you the pendulum's 1 meter and the opposite is 0.5. So that's how I messed up over there. So how do you find the theta? Let's do number 2. Well, sine is opposite and hypotenuse. So the opposite is 0.5 meters, and the length of the pendulum is it's a 1 meter pendulum, so the hypotenuse is 1. The inverse sine of that's 0.5. Inverse sine of 0.5 is 30 degrees. So there you go. Find the tension T using, well, this is actually all that we did up here. That's what we did up there. Okay. So find the velocity. Let's go back. Tan theta. Our equation's tan theta equals v squared over g r. So tan 30 degrees equals v squared divided by, it's 10 meters per second squared on this planet, times r is, we're told it's 1.00 meters. So we got to find tan theta. Let's get a little sloppy. Let's fix that. And tan theta with a 57735 equals v squared. Well, wait a second, I made a mistake there. this radius is not 1. The radius, you can see over here, of the circle is, remember the diameter of the circle, it's a 1 meter circle. And so the radius is 0.5. That's a mistake. 50. Okay. 10 times 0.5 is 5. Multiply both sides by, so get that 0.57735 cross multiply times 5 equals square root is 1 point. So the velocity is 1 point. Yeah. 1 point. Okay, we'll call it 1.69 meters per second. 3 significant digits. What's the period? Well, for a circle, the velocity for a circle is 2 pi r. Period is capital T. So the v times t, let's see, yeah, v times capital T is 2 pi r. Divide both sides by v, that you just found, right? Cross that out, divided by v. And so let's do 2 pi r. Remember the radius is 2, so 2 times, I'll call it 3.14 times 0.5, which is the radius, divided by 1.69, and you get the I'm getting 1.86. The t, the time to go one time around, that's what its period is. Any time, continuing cycle, 1.8, I'm getting 1.86 seconds. Okay, that is the conical pendulum. A pendulum that is moving. And you know what we never talked about, and I should have, and I should add to this. Ready? Conical pendulum moving with a speed is constant. Now you should be able to tell the speed is constant because it's a circle. It's a constant radius. And the angle doesn't change. The angle is a single angle, so the horizontal component of the tension doesn't change. If the centripetal force doesn't change, then the mass doesn't change, then the r doesn't change. The speed is constant. So you probably should have been able to figure that out, since the radius is the same, the mass is the same, and the tension is the same. The speed is constant. But I should have put that down. So it should be a pendulum moving in a circle at constant speed, not constant velocity, but constant speed. And that is it.